So, we will now continue again with our discussion on tensors. So, before we introduce anything new, I will just start with an erratum of what we were doing yesterday. That was to do with the way I drew my coordinate system. And if you see the coordinate system that I have drawn out here, it has a coordinate axis which is 1, there is a coordinate axis 2, and the way I have drawn my coordinate axis 3, which is supposed to be given by this relation, is incorrect. Incorrect in a sense that this is not the right-handed coordinate system that we use. So, in a right-handed coordinate system, I will have E1, E2, and then E3 would actually be coming out of the screen. So, this is also something which actually incidentally helps us in our next discussion, that why do we care or why does it matter to reflect on this point of a left-handed and a right-handed coordinate system. So, we have so far been seeing about vectors, and we also got introduced to this quantity of tensors, but before we take this any further, it is important to just have this discussion on the coordinate system. So, I will draw a coordinate system which is my right-handed coordinate system, and I will draw a coordinate system which is a left-handed coordinate system. So, now if you were to look at objects, let us say velocity. So, you have a particular point in space which was moving with a velocity u, and you knew its position vector from the reference origin. That gives us what would be its distance from the origin in terms of the separation vector. Now, you can use this in order to actually calculate what would be its let us say quantities like angular momentum. You can actually try to compute what would be the angular momentum of this particular object, given that it is moving with a velocity u at a certain distance r from the origin. So, now if we use the relation of what we know for angular momentum, so if I write down what is my so I have the linear momentum mu, which is now a moment about the origin that gives me my angular momentum. So, now if I am trying to compute what would be the angular momentum that is there in this particular problem, the angular momentum about that origin for this particular particle that is moving with velocity u is going to be coming out of the screen. So, if I am using a right-handed coordinate system, so in the right-handed coordinate system, basically it is in a sense which is pointing along the +3 direction. Now, if you do that same exercise in the left-handed coordinate system, in the left-handed coordinate system, if you now try to compute the same quantity of the same body which is moving with a velocity u maintained at a distance of r from the origin, and try to find out what would be its angular momentum, the angular momentum is now going to switch a sign. So, what you see here is that quantities like velocity, quantities like position, they do not care about whether you are choosing a left or a right-handed coordinate system. But objects like angular momentum, torque, angular velocity, these are going to actually sense or care about what would be your choice of handedness. Another way to see this is if you consider looking at a vehicle from behind. So, just to make sure that I have a distinguishing feature of the vehicle, I will draw with one side, the left side, that I am staring the vehicle from behind, and I am seeing the two wheels from the back side. The wheels are actually spinning. So, now if I want to again compute what is the angular momentum, if the vehicle is moving forward, I will have the angular momentum for both the wheels pointing to the left. Now, if I reflect this, if I do a reflection, which means what was the wheel that was on the right side now switches sign. So, also for the wheels I am going to basically do the same thing, just to make sure that there is some pattern for us to distinguish which was left and which was right. So, now if you look at this particular scenario, when you have done a reflection about an axis that is drawn here, separating out the passing, let us say passing through on the right of the vehicle, the angular momentum will not switch. So, you have done a reflection, the angular momentum, instead of actually getting reflected, continues to maintain the same sense, which says that unlike other vectors, which if when you do a reflection would get reflected, there are vectors like angular momentum, there are vectors like angular velocity, there are vectors like torque which behave differently. So, the transformation or the rotation that we were discussing earlier. So, we had this particular object that we got introduced earlier. So, this is related to what you will see elsewhere as the rotation matrix. So, the rotation matrix. So, if I say that the prime variable written in this manner, we were writing it yesterday when we wrote it in terms of the direction cosines, we wrote it in this manner. So, the rotation matrix tells us that how the components of a vector undergo a transformation due to rotation of an axis, all the three axes when they are rotated. But instead of rotation, there is another orthogonal transformation that you can do, which is reflection. So, let us say that the a simple two-dimensional reflection would be that you multiply with 1 0 0 minus 1, which means your x coordinate remains the same, the y coordinate flips. So, when you have this reflection, a vector which does not undergo a change of sign due to reflection, that is what we are now going to give a name to it. Those are known as true vectors. They are also called polar vectors. So, this would be what is your objects that you are encountered: velocity, linear momentum, and things like force. And the ones which undergo a switch of sign, they are known as pseudo or axial vectors. So, this would be the counterparts of angular momentum, torque and similar quantities, which would usually come about when you are trying to take a cross product or take a curl. So, whenever you do a cross product, you have to choose a handedness of the coordinate system, and this handedness basically decides that there are certain objects which care about the handedness, those are pseudo vectors, and certain objects which are deciding whether you have a true vector. So, the transformation that I wrote for a vector, that A is L transpose, or A prime is A transpose dot L transpose dot A, that how a vector transforms. This is actually for true vectors. For a pseudo vector, it would be determinant of L, L transpose dot A. Now, if you recall from our previous discussion, we said that, sorry, I have been using C. So, let me just so determinant of C multiplied by C transpose dot A. Now, if you remember from what we discussed in the earlier lecture, is that C transpose is the inverse of C, which means that determinant of C square is 1, or determinant of C is equal to plus or minus 1. So, plus 1 signifies rotation, whereas minus 1 is reflection, or what will generally be called as improper rotation, which means you are doing a combination of rotation and reflection. So, the negative sign for that determinant comes about when you are doing a reflection. You can see this from this simple reflection matrix that I wrote down, 1 0 0 minus 1. It's a diagonal matrix, and for this diagonal matrix the determinant would be minus 1. So, this exercise actually shows that if you have a pseudo vector, then if there is an improper rotation, then determinant of C is going to be minus 1, in which case it picks up a negative sign. If you are just doing a coordinate rotation, just a pure rotation or a proper rotation, then it does not matter. The true vector and the pseudo vector, basically there is nothing to distinguish in terms of how its components are going to transform. The distinction comes when you are actually doing a reflection or an improper rotation. Now, does this have any physical connection? Does this help us in anything to do with the actual mechanics of the problem when we are going to understand these things deeper, or is it purely in terms of a classification that is more mathematical? So, this is a part which we will occasionally take help of, and it becomes more and more useful as you get further deeper into continuum mechanics. Is on many occasions you are going to infer relationship between quantities. So, you are going to say that let us say I am doing a problem where the force, I am trying to find out whether it is going to be proportional to the velocity, the angular velocity, and what should be the relation. So, let us say we are doing a problem, I will give you an example that we want to find the drag on an object, arbitrary shaped object, and let us say the dynamics is governed by very viscous flow. We will see these things a little bit more formally, but for the time being you can imagine that the problem is linear, which means that the force that the body experiences should linearly depend on its translational and angular velocity. That is basically what we are told based on the linearity. Now, from the knowledge that we have just gained of tensors and true vectors and pseudo vectors, can we construct something in terms of the relation involving the force in terms of velocity and angular velocity? So, if I just start with a very simple relation saying that okay, force is a vector, velocity is a vector. So, I will just choose some scalar and write it in this manner. This scalar is what you might require a detailed calculation. But if I were to write it in this manner, so let us call this C1, omega, I am violating the property of true and pseudo vector. If this relation was true in terms of that there is a pure constant, you would immediately argue this is impossible purely on the grounds that the left hand side is a true vector, the right hand side is a pseudo vector. So, if you do a reflection of the coordinate system, the left hand side will not pick a sign, but the right hand side would pick a sign. So, this is not possible. You cannot have this kind of a scenario arising in the problem. But then if I do not have a linearity, this again is something which will come up much later, but you can have a force which can take a form of this, which can take a form of this kind. This usually is what is called as a lift force. It will be something which we will dwell on later, but right now purely from an expression point of view, this expression is consistent. Why is it consistent? Because I have a pseudoness that comes from the angular velocity, omega is the spin or the angular velocity, and I also have a pseudoness that comes from the cross product. So, which means there is a determinant of C being which is related to the rotation matrix or the transformation matrix, and the cross product also has a determinant of C that comes in. So, this entire exercise gives me a determinant of C square which is plus 1. So, when you have anywhere you have a cross product, it automatically tells you that there can be a pseudo vector, and then when you have the angular velocity, that is another pseudoness in the problem if you say so, and which tells us that this is a valid mathematical expression because the left hand side is a true vector, the right hand side also is a true vector, whereas the second line is an invalid expression irrespective of whatever you do in order to find C2. At the starting point itself, you cannot have something of this sort. You cannot have a relationship which tells that force is linearly proportional to the angular velocity, with a scalar multiple, because it's just violating the fact of how these objects are going to transform under reflection. So this is the part which is very helpful when you are trying to actually construct what is the potential solution of a problem. Like you want to find out that given an arbitrary object with adequate amount of information that I have, before I set out doing the calculation, can I make an informed guess regarding how certain quantities are related to some other quantities. Let's say the mechanical response in terms of deformation, velocities, etc. So you should not agree to a relation where you have pseudo quantities related to a true quantity. So pseudo quantities, obviously you know that if it was the torque which was there, the torque can be proportional to the angular velocity in a linear manner. This is valid because both the LHS and RHS are pseudo vectors. But similarly, this expression is not valid, that the torque cannot be linearly proportional with a scalar multiple multiplying the linear velocity, because the right hand side is a true vector, the left hand side is a pseudo vector. So even before you set out actually solving problems, knowing these tensorial properties are very helpful. So we now have some idea regarding what true vectors are, what pseudo vectors are, and we have gotten introduced to this quantity, which is an object that has two indices. So this is now giving us a more general setting of what we call as second order tensors. And as I said, you can now universalize this thing by saying that, okay, a vector is actually a first order tensor, and if you just have a scalar, that would be a zeroth order tensor. Now similarly, you can realize that there is nothing that stops you here. You can have more number of indices that appear. So you can have an object that has 3 indices, and this would be a third order tensor. So before you move to third order tensor, let's spend some time regarding the second order tensor. We just got introduced to the second order tensor, and we also saw this particular property that a second order tensor, if I am looking at its transformation, the transformation basically would follow this relation with the rotation matrix. So you will have each component of the tensor now changing due to the coordinate transformation. So now, since this has 2 indices, it's often useful to think of them in terms of matrices. You can always say, okay, I have a second order tensor in 3 dimension, which means I can write this down as a matrix whose components are arranged in terms of rows and columns, where each element of that particular matrix are the indices taking values from 1 to 3. So you can explicitly write it in this particular matrix form. So for second order tensor, it's always convenient if you just think of them as matrices if you are getting introduced to this idea. Gradually you will find the matrix idea not any further necessary in order for you to understand tensors as you go to higher order. But in the beginning, understanding first order tensors where you are looking at vectors as row vectors or column vectors, and then subsequently second order tensors as matrices is a good starting point. So now when you know matrices, you know that matrices in general can be classified as symmetric matrices. So here we are interested in tensors, so I write them as symmetric tensors. So what would be symmetric tensors? Symmetric tensors would be where all the off diagonal elements, their counterparts would be equal. So the symmetric counterpart of that would be A11, A12, A13, and then A12, A22, this should have been 23, 23, A23, sorry, this is A13, this is A23, and this is A33. So the off diagonal elements are all equal, and obviously it has a set of diagonal entries. So this is a symmetric tensor. Just like you would have learned symmetric matrices in the past, you now have a symmetric tensor. The simplest symmetric tensor that you probably already saw, but maybe we didn't use the terminology tensor then, is the Kronecker delta, delta ij. This in matrix language is an identity matrix, because if you write down delta ij, it has elements of 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, similar to symmetric matrices that you have symmetric tensors, you also can have anti-symmetric tensors. Anti-symmetric tensors are tensors where aij is equal to minus aji, which means, now if you write this down, the first thing that you observe is if aij is equal to minus aji, let's take I equal to j. So let's take a11, which means a11 is equal to minus a11. And this only has a trivial solution, the solution being that a11 has to be 0, which means all the diagonal elements for an antisymmetric tensor would be 0. And then I have a12, a13, a23 and minus a12, minus a13, minus a23. So we have classified tensors in terms of symmetric and antisymmetric tensors. Now in general, just like any matrix need not always be symmetric or antisymmetric, similarly every tensor need not be symmetric and antisymmetric. So what we can do instead is we can take any arbitrary matrix. If I again write it as aij, I can write it as aij plus aji and then aij minus aji, which means every tensor I can split it into a part that is symmetric and I can also split it into a part that is antisymmetric. Now this is something which becomes quite handy when we are going to do problems in fluid mechanics. So we already saw quantities like divergence of velocity. We also saw quantities which are the curl of a velocity. We have explicitly written this down. There will be a quantity which we will get introduced to, which will be the gradient of velocity. So gradient of a scalar function, of any scalar function, if I write down, that would be dou f, dou phi, dou x1, dou phi, dou x2, dou phi, dou x3. x1, x2, x3 are those coordinates. The gradient of any vector field would actually be quantities that are dou v1, dou x1, dou v1, dou x2, dou v1, dou x3, dou v2, dou x1, dou v2, dou x2, dou v2, dou x3, dou v3, dou x1, dou v3, dou x2 and dou v3, dou x3. So it would have all the 9 components instead of just writing it for the scalar where you just have a single term. So which is to say that the gradient of v, if I am writing its ijth component, the gradient of v would be dou vj. In this notation I am writing it as dou vi, dou v, dou xj. Now what I can do here, because this is arbitrarily not necessarily symmetric or antisymmetric, what I can do here, I can write this as half dou vi dou xj plus dou vj dou xi and then dou vi dou xj and dou vj dou xi. So the velocity gradient, which is a quantity that is of immense interest when we do fluid mechanics, actually has a part that is symmetric and a part that is anti-symmetric. And this is going to be something very crucial when we move to the next topic, which would be trying to understand the kinematics of a flow, and then from the kinematics of the flow trying to infer about the deformation that is occurring. That if I say that I have the velocity changing spatially, the information which captures the spatial variation of velocity is the velocity gradient, and that is a tensor of second order. So, that tensor of second order has a symmetric part and has an antisymmetric part. The symmetric and antisymmetric part is something that is at the fundamental backbone of understanding how we think of deformation that occurs in fluid. So, we are just writing this right now, but we will revisit this when we go back to when we start the topic on kinematics. So, we saw this property that we have for symmetric and antisymmetric tensor. Now, there is another interesting property that comes about when we are dealing with symmetric and antisymmetric tensor, is that if I say that I have a symmetric tensor Bij and an antisymmetric tensor, let me use a different Eij equals minus Eji, I can look at this quantity Bij Eij. Now, what is Bij Eij? First question is it a vector, is it a second order tensor, or is it something else? Now, again, if you use Einstein summation convention to understand this, you see that there are two repeated indices here. There is a repeated index I, there is a repeated index j. So, this object is actually what is a double contraction of both the indices. So, every time you do a contraction of indices, contraction basically is the language of saying what you have done as a dot product. So, every time you have repeated indices, you are going to lose an order. So, Bij EKL, this is an object that has 1, 2, 3, 4. There are 4 free indices. Bij Ejk, this has 2 repeated indices, but only 2 free indices. So, here you have 2 free indices. But here Bij Eij, there are no free indices. All the indices that you have here, they are all repeated indices. So, this is equivalent to B, not the usual dot product or matrix multiplication, but a double dot product with E transpose. Why E transpose? Because B double dotted with E would be Bij Eji. So, you are first going to do a dot product of the nearest indices, then the outer indices. So, B double dotted with E would be Bij Eji. So, Bij Eij is B double dotted with E transpose. So, what we want to do now is, this is for a general tensor, not necessarily symmetric or antisymmetric. But now, let us say that B was symmetric and E was antisymmetric. What would happen? So, if B was symmetric and E was antisymmetric, if I am trying to compute the term Bij Eij, since B is symmetric, I can write this as Bji. There is no distinction between Bij and Bji, they are one and the same. But Eij is not the same as Eji, it picks a minus sign. So, it is minus Eji. So, what you have here on the LHS is Bij Eij, and on the RHS you have Bji Eji. Now, we go back to what we learnt about repeated indices. For repeated indices, there is nothing sacred about what you label that index. about that index level. Which means if I have called this as j and I could have called this as I, j as I and I as j. There is nothing sacred about calling that index, the first one as j and the next one as I. I might as well just call the first one as I and the next one as j. So, which gives me minus bij eij, and on the LHS it is bij eij. So, you have a scalar on the LHS which is equal to negative of itself. That means that this object is 0. So, this again is going to be quite useful. We will keep doing a callback to this particular property, that a double contraction of a symmetric and an antisymmetric tensor is always going to be 0. Whenever you do this product, you are always going to get this to be 0, and this is something which we are going to start using quite frequently. So, that was about the property of symmetric and antisymmetric tensors. The other, so delta ij that we got introduced to, this was a symmetric tensor. The antisymmetric tensor that we got introduced to is epsilon ijk. Why so? If I were to switch indices, so epsilon 1, 2, 3, if I switch 2 with 1, it will pick a minus sign. So, whenever I am switching any two indices, so here when you are talking about symmetricity, you are talking about symmetricity or antisymmetricity with respect to a pair of indices. So, epsilon ijk, the permutation symbol, is a tensor which has 3 indices. So, this is a third order tensor, and this third order tensor is antisymmetric. You pick any pair of indices here and you switch those indices, you are basically going to pick up a negative sign. Epsilon 3, 2, 1 is going to be minus epsilon 3, 1, 2. And if you want, you can do this once more, minus of minus epsilon 3, 2, 1. So, that is a trivial statement, you recover the same thing. So, every time you make a index hop one location, so you switch between 2 and 1, you pick a minus sign. You switch between 1 and 3, so if you write epsilon 3, 2, 1, that is minus epsilon 3, 1, 2. Now, you make 1 and 3 switch places, it will be minus of minus epsilon 1, 3, 2, which is plus epsilon 1, 3, 2. And this, if you write 1, 2, 3 in that cyclic order, we know 1, 2, 3 is the same as 2, 3, 1, which is the same as 3, 1, 2. Similarly, in that same 3, 2, 1 will be minus and 1, 3, 2 will also be minus. So, they are basically both going in the same anticyclic manner. So, this is just to say that you now have already seen objects that are symmetric, objects that are antisymmetric, and you have also seen objects that are of order 2, objects that are of order 3. While doing the dot product, while doing the cross product, the idea was to introduce these two crucial objects, which are things that have representation with multiple indices and also has this particular properties of being symmetric and antisymmetric. The next property which we will be using for tensors is the property of isotropy. So, isotropic tensors would be tensors whose components remain unchanged under coordinate transformation. So, you do a coordinate transformation and you ask the question, would the coordinates change? So, for instance, let us start from a scalar. So, I have a temperature that is defined at a particular point in space x1, x2, x3. So, in this room I have decided that coordinate system, which is, let us say, the right corner of this room, where I have designed my coordinate system and I measure the temperature at a particular point. If I change my coordinate system, I choose, let us say, the left corner of the room, or a coordinate system that is rotated at an angle 45 degree. So, at that same location where I have measured the temperature would be exactly the same in the new coordinate system. So, this is not something very profound. This is something which you already are used to in thinking, but you may not have put a name to it, that any scalar doesn't care about what is your coordinate system. The value of a scalar at a given point is independent of how you transform your coordinate system. So, this is to say that all scalars, or what we are giving a slightly fancy name now, all 0th order tensor are isotropic. So, the idea of isotropy is basically universal when you are talking about scalars. What about vectors? So, for vectors we already saw that the relation is, if I have a vector that is defined in a coordinate system, which is 1, 2, 3, and now I have one prime, 2 prime, 3 prime. So, now the question is that will the components of a vector change under coordinate transformation? Let us say I did the same thing as I said earlier, that I chose a corner of the room and I am basically trying to find out what is the velocity vector or what is the position vector at a particular location. Now, that obviously cares, because if I write down the component of the position vector or the velocity vector at a particular location, it does change as you do a change of coordinates. So, with coordinate transformation it is going to change. So, what does it mean? Are there no vectors that would actually remain invariant under coordinate transformation? And then you see, if you look at this, the only vector which would satisfy this would be the trivial solution or the null vector, a vector whose components are 0, 0, 0. That is the trivial solution. And you can see that this is true for any order of tensor. Any tensor which is a null tensor, all component being 0, will trivially not change if you do a coordinate transformation. Because what a coordinate transformation is basically doing is, it is doing a linear mapping of the components of that particular quantity to the new coordinate system. So, if you have all elements being 0, they will continue to remain 0, nothing will change. So, that is the trivial answer, which means that there are no isotropic vectors other than the null vector. Now, what about tensors of rank 2 or order 2? So, we saw that this one Aij prime is related to C transpose Ik Akm Cmj or Cki Akm Cmj. Now, we are interested in the non-trivial solution. Are there any non-trivial isotropic tensors? And you can now check this in various ways. I will check this using a substitution, or rather a validation here. What about if I consider the Kronecker delta, the identity matrix? So, if I plug it into my equation, so I had, this is my transformation rule for a rank 2 or order 2 tensor. So, if I say that A is identity, then I have, this is basically 1 0 0 0 1 0 0 0 1. So, if I take delta dot C, that is going to be C. And we know that this is an orthogonal transformation, which means C transpose is nothing but C inverse, which means this is the same identity transformation or identity matrix. So, the Kronecker delta is, and it turns out, the only isotropic order 2 tensor. So, the fact that it is only requires you to actually do a little bit more work to say that let us assume that there is something else, there is some other tensor which is over and above the delta ij that is also isotropic, and you try to show that if it is distinct from delta ij, and it turns out it is not. So, I am going to leave that proof here. For those interested, you can check the book on tensors by Rutherford Harris, where the proof is given. But right now I am going to state it without a formal proof, that there is all scalars are isotropic, there are no non-trivial vectors that are isotropic, and the Kronecker delta or the identity tensor is the only isotropic rank 2 tensor. I am using the word rank and order interchangeably here. So, it is to say that you have how many, if you write it in the matrix form, what would be the rank of that particular object. Now, what about the order 3? Again, this is going to be without a formal proof. Epsilon ijk, and you can again write down the transformation rule for a third order tensor, and epsilon ijk is the order 3 isotropic tensor. So, we had delta ij as the isotropic order 2 tensor, and epsilon ijk is the isotropic order 3 tensor, and we know there are no order 1 or vectors which are isotropic other than the null vector. Now, what if we keep going beyond? You can ask, what about isotropic order 4 tensor? Now, here again an isotropic order 4 tensor would be having 4 indices q, I, j, k, l, and this incidentally is only expressible in terms of order 2 tensor. So, there are no order 4 tensors by itself, it is purely in terms of order 2 tensors, which means it will be delta ij delta kl, delta ik delta jl, and delta il delta jk, and these would have some arbitrary constants. Because here I can always multiply these with some constant and they would continue to be isotropic, because we know a scalar is always isotropic. So, if I take the identity matrix and multiply it with some number, that is also an isotropic quantity. So, the isotropy continues to be the same even if it is multiplied by some scalar quantity. Now, for an order 4 tensor, there are no separate order 4 tensors. Whatever you have is basically a combination, a linear combination of the order 2 tensor products. So, delta ij delta kl, there are 4 free indices here. These are isotropic. So, that is your order 4 tensor. There is another order 4 tensor, and then there is the other order 4 tensor. So, you have a linear combination here. So, we will primarily restrict ourselves to order 4, because order 4 is typically what you will encounter in most cases in fluid mechanics. So, we will see an example of order 4 tensor in some time when we start getting introduced to how we write down viscous flow equations, but this is an important equation, or rather formulation, that we are going to come back to, that what is the most general order 4 tensor. The most general order 4 tensor is going to take this particular form. So, you can again ask, like where would these things be relevant? I mentioned the constitutive model, but is there any other place that you think that these things are going to play a role? I mean, where you might be interested in doing this. So, in several places where you are not able to direct calculation, let us say one example is what I will give you, that you are trying to find out what is, we got introduced to this object, dou uy, dou xj, that's the velocity gradient. Now you are interested in actually calculating the correlation of this quantity in a turbulent flow. I put angle brackets here. If you haven't come across turbulence, don't bother too much. You can think of this angular bracket as doing some kind of an averaging. So you are trying to find out what is the average correlation between velocity gradient quantities. So for instance, this could have terms like dou u1, dou x1, dou u3, dou x2. It could also have terms like dou u2, dou x1 square. It could also have terms like dou u2, dou x3, dou u1, dou x2. All combinations are there. So you are looking at how these velocity gradient quantities are correlated and you are trying to do an average. And this is something which you obviously cannot find in any closed form analytical calculation. You are doing it in a very completely nonlinear problem. But what you know about the problem is that this problem is homogeneous and isotropic. So this is something which you will come across when you study turbulence, that there are flows where the turbulence is homogeneous and isotropic, which isotropy basically, mathematically what we learnt here means that you don't have any component changing due to coordinate transformation. The other way of thinking of isotropy is that there is no preferential behavior in some angular manner. So if I were to actually look at properties in a particular direction, what direction I am basically inspecting doesn't matter. So if I ask the question that I want to find out what is the density of air in this particular room, if the density of the air was very well mixed, whether I am making measurements at an angle that is, let's say, I define a particular direction and I make it a 30-degree angle, a 40-degree angle or a 120-degree angle, it doesn't matter what's my direction. Similarly, I can have a quantity which is homogeneous, which means point-wise there is no spatial variation. So when you have isotropy, before you do anything, before you do any calculation, you know that this object, this complicated velocity gradient correlation can only have this particular form. So even though there are 4 indices, so when you have a 4th order tensor, the number of components for a 4th order tensor would be 3 to the power 4, which is 81. So you don't need 81 components. You only need 3 components. So this is one part which is beautiful, that if you have an isotropic order 2 tensor, an isotropic order 2 tensor will have 9 components. I mean, an order 2 tensor will have 9 components, but an isotropic order 2 tensor, if you are looking at what is something that is isotropic, that only has 1 independent component. An isotropic order 3 tensor can have 27 for a general order 3 tensor, but if it is isotropic, it's going to only have 1 independent quantity to be specified. So when you go for the 4th order, even though there are 81 components for an order 4 tensor, you only need to specify 3 quantities independently. So this simplifies your calculation of whatever you are going to do. So if you are doing these experimentally, if you are doing these numerically, you don't need to go about actually finding 81 components, because that is actually disregarding what you know about the properties of that tensorial quantity. You are trying to calculate a tensorial quantity which is order 4. That doesn't mean that you need to go searching for 81 terms in that problem. Your experiments or your numerics should be targeted at only finding 3 independent quantities. So this is basically what we have now for isotropy. So we'll still need a little bit more time to finish this. So the next class I'm going to actually discuss that now that we have a formalism for what are isotropic tensors, what are symmetric and antisymmetric tensors, we will take this and then try to actually look at few vector calculus identities and see how tensor analysis helps us.